Okay, welcome. So I'm here recording our first content based lecture for the physics class. I'm going to go ahead and share my screen. Basically, how I'm going to do this is I've got two computers in the Zoom room, and I'm recording it via Zoom. I just kind of find that easier to share my tablet, and then you can kind of see what I'm writing along with that. So sharing the screen now. And what I'm going to do is what we're going to be covering today. I'm going to have a little bit about sort of the just an introduction to physics and more broadly the kind of obligatory introduction to the scientific method, but I'm going to put my own little twist on that. Then we'll discuss something a bit on measurement and measurement reporting, so some measurement units, things you'll want to know, measurement reporting, and then getting into the rules for significant figures. Now I tend not to be as, I'll just say this up front, I tend not to be as hard on or as gung-ho on significant figures as as some people. And I'll get into why that's the case. But before we get there, let's start off with just talk about why physics. So the idea here is that this is a general education science class. So why physics? Why do we talk about why do we do this science and not like chemistry or biology? And you know, it's a reasonable question, but I think physics is a pretty good in studying physics, even at the level we're going to cover it, which is not getting into a lot of the nuance of the topic and a lot of the difficulties of the subject. Physics can show, it can encapsulate the scientific method pretty well. Um, and 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 the idea here is, and I'll get into more of that, but the idea is that you can kind of reduce a lot of complicated systems into something that's kind of simple, and that like I said, you can understand using not super easy math, but also not insanely difficult math. And so we can kind of go through the entire process in microcosm in physics, and that's kind of why why I think physics is it tends to be a common selection for this type of class, for this kind of survey level general education science class. So what I want to talk about first of all is so just make a note of that. It's a good microcosm for scientific method. Now, what I'm going to do, I'm going to put in the scientific method graphic that I'm sure you've seen before. So I'm going to do this in kind of a different way. So copy that, and then we'll put that over here. Right, and there it is. All right, sweet. Okay, so if you've ever seen the scientific method, it kind of looks like that. You may have seen this kind of diagram, and it starts with ask a question, do background research, construct a hypothesis, test one experiment, analyze results, draw a conclusion, and then you decide if your hypothesis is true or false. And then you report your results. If your hypothesis is false, you go back and you turn this into a cycle and you repeat again. I have never been a huge fan of these diagrams. I think they really do, they oversimplify the scientific method to something that's to they make it seem like it's first this, then that, then this, and really I don't really think that's what it is. And furthermore, I don't really think this diagram captures what you're really trying to do. It doesn't really capture the goal of performing science, and what is it you're really trying to get after here. So I'm not never really been a big fan of this, and one of my first reasons is that this leaves out observation. Um, and really, you don't get science without observation. Okay, so every scientific endeavor, whether it's a hard science like we're covering in physics, A life science, also sometimes considered hard sciences, but life sciences can be a little more nebulous. It's a social science. It always starts with observation. You can't do science without observation. Now, maybe that's encapsulated in background research, but I really don't think so. In order to do good science, you have to make observations. And really, you could also say that maybe this in the testing with experiment is when the observations come in. But I really don't think you would wait until that point to question mark there. I don't really think you would wait until that point to start making observations. You basically, observations are what actually inform the questions. That you just go and you see something interesting in the world, that's something that you don't really quite understand why it happens that way. And that is ultimately what leads you to the question. So I don't want to say that my take on this is the gospel, it's the end all be all, but I'm going to give you a slightly different take than usually comes in this little diagram, and I'm going to tell you sort of how I think about these things. And again, some people might disagree, some people might partially agree, but this is sort of how I think about it. Fundamentally, what I think science is about, I'll just state it right here. Science is about constructing models. Okay. Now that I think that's the basic activity that we do in science. Now, what is a model? By this I don't mean a computer model. Basically, what I mean is a model is just a simplified representation of a phenomena. Okay. And the idea is that taking into account of a phenomena or phenomena, could be multiple phenomena. Models can encapsulate multiple phenomena. And the idea here is that the world is complicated. We look around at the world and we're not really, absent, a body of knowledge, and largely many times scientific knowledge, we don't really know why things work the way they do. We might have guesses, we might have traditions that say certain things, but we don't really know, why that's the case. And basically what a model is, it's taking a complicated set of phenomena, the complicated world, and it's simplifying it into terms that are that we can more easily grasp. And part of what this does is this simplified representation allows you to make predictions. Okay. And really, another way of putting this is it allows you to generate hypotheses. All right. And basically, if you've heard the term hypothesis, this is one of the most, I think, hypotheses, one of the most misused terms when talking about science. A lot of times people say, what's a hypothesis? They'll say it's an educated guess. Well, not sort of, like, you can think about a hypothesis in that sense, but really the way I think about hypotheses, it's a prediction that is made by the causal explanations that a model is proposing. Okay. So really that's more what a hypothesis is. It really is a prediction about what is going to happen based on the model you have of some sort of representation. So hypothesis, the way I think about this is a prediction based on the model. Now, there are differing schools of thought as to how you should treat hypotheses. In that diagram, you'll see you have two options: either the hypothesis is true or the hypothesis is false. And what a lot of scientists don't like phrasing it that way. The hypothesis being true, what you would say is that the hypothesis was confirmed. Now the as to whether or not that's true, what you are trying to validate, or in many times invalidate, is actually the model. It's not the hypothesis per se. You're trying to say, okay, does this model generate good predictions, or does this model fail to generate predictions? And a lot of times what the hypothesis will do is it will either most scientists don't think hypotheses prove models. They think they can disprove models. So if your hypothesis is rejected, then the model is disproven. I also think that's a little bit inaccurate. A lot of times what having a hypothesis disproven does is it shows the limits of the model. So an example of this would be Newton's laws of motion. They don't work. They start to break down at very high speeds and at very small sizes and at very high gravitational fields. And the idea is that some people will say, well, that disproves Newton's laws. And I would say that's not quite right. What that did is it proved the limits of the model. Okay. And really, no model is ever complete unless you know its limits. And a lot of times the limits aren't known when the model is first proposed. It's the model is proposed based on a set of observations, but it's not really known, how well this simplified picture is going to bear out. And as we know, most simplified pictures, when you start looking into more and more detail, they will eventually break down. That's just the nature of trying to have a simplified representation of something. So the idea here is that a lot of times what hypotheses will do is they'll prove the limits of the model. They'll prove the scope of the model. And that's one way to think about it. Now, some people think that from hypotheses you get laws. Once hypotheses are proven correct, they become laws. Not so much. What I think is that models, laws, these are theories. Hypotheses become theories. Laws are different. I misspoke there. But what the way I think about theory, some people say when something is proven over and over again, it goes from hypothesis to theory. I don't quite agree with that. I think a hypothesis is something you use to test a model. And a theory is a model that has been reliably tested in many different ways. So what I would say about a theory is it is a model that has generated reliable predictions consistently. Now, another thing I like to think about with when discussing a theory, and this isn't necessarily you don't necessarily need this for it to be a theory. It becomes a theory when the model generates reliable predictions. But there's more to that. But another thing about the theory is that the theory also, oftentimes a theory is the boundaries of the theory. So the boundaries of the model are well known. Now I'll put this in parentheses because this isn't entirely true. Many theories, the limits of the theory are not entirely well known. But oftentimes when it does get elevated to a theory, to the level of a theory, it's at least in scientific parlance. You can use theory colloquially. It's a much more nebulous term, but in scientific parlance, when something is elevated to a theory, people have started to understand the limits of where it applies and where it doesn't apply. Okay. Now, a law, the way I think about a law is that this is a mathematical description of specific phenomena. So the idea here is that if we have something like the theory of gravity, basically what the theory of gravity is going to include, it's going to include that things like the idea that mass generates a gravitational field. So anything with mass has its own say mass generates gravity. Mass it responds to gravity as well. So gravitational fields attract masses. It does all of these things, and then gravity decreases over distance. These are things that would be included. Now, in the theory of gravity, theory of Newtonian gravity, there are other theories of gravity. And again, these other theories of gravity, like a relativistic theory of gravity, it does not prove Newtonian gravity incorrect. Basically, what the relativistic theories of gravity do is they prove the limits of where Newtonian gravity applies. Or they describe the limits of where Newtonian gravity applies. So decreases over distance. These, and you could go on with things that the theory of gravity contains. Now, alternatively, you could have the law of universal gravitation. And basically what this is the mathematical statement that encapsulates many of these things that are contained within the theory of gravity. So the law of universal gravitation, you don't need to memorize this, at least not for the moment, but it looks like this. The force of gravity between two massive objects, it's the product of the two masses times some constant g. A lot of times that constant g is written out front. These constants in physics, basically what they do is they keep track of units. So it's worth keeping in mind. Divided by the distance, and I'll use R12, the distance between the two objects squared. Okay, so that was the law of universal gravitation right there. And so that's the difference sort of between the theory and the law associated with gravity. Okay, so that is basically what I wanted to do about just kind of my take on the scientific method and what some of these terms mean. Not super relevant, but worth knowing and worth thinking about if this kind of thing interests you. So what I'm going to jump into next is, and part of the reason I wanted to do this is because measurement relates to how these things are determined. And the way I think about measurement is really, it's really just quantification of observations. Now, sometimes people will talk about qualitative measurements. I don't think that's quite correct. What you can have is you can have non-numeric measurements. And if you think about something like a non-numeric measurement, that would be like a ranking. So be like, which do you like more, gummy worms or gummy bears, say? And maybe you have no preference on that, but the idea is that is a measurement, but there's no real number associated with that measurement. It's just one or the other. Now you could try to associate numbers with those measurements. They may or may not be meaningful, but I tend to think of those as sort of ranking based measurements, but they are still measurements. Now in physics, what we are going to do is we're going to use we're going to be looking for quantities that we can measure numerically. Okay. So that we can quantify numerically. And so the idea about measurement is what you're really doing is you're comparing an observation to a known standard. Okay. Now, again, some of these known standards can be easily represented by a number. Sometimes they cannot. Okay. Now, the main quantities, the basic quantities that we'll be looking at, basic quantities to be measured. They're as follows. So time is one of the most fundamental one of the most fundamental quantities. Some people they like to kind of have this profound time is an illusion statement. I absolutely disagree. Time is not an illusion. You can observe the intervals between causal relationships, and these things are comparable, and they can be quantified independent of a human perception of it. So the idea is that you can compare, say, how quickly a glacier moves to how quickly a volcano explodes. Okay, these are both causal processes, and you can compare the time interval between those two, and that's kind of what time is. Now, another quantity is length. And fundamentally, what length is, it's measuring spatial relationships. And again, the idea is that entities exist at different points in space, and you can quantify their locations in space, their distances relative to one another, using this idea of length. Another one is mass. Okay. Now, mass is a little bit more complicated. The way we think about mass, we'll get into mass quite a bit more as we discuss this. Some people, again, they like to say, well, we don't know what the heck mass is. Mass is a fundamental attribute of entities. As far as we know, well, that's not quite correct, but mass is an attribute of many entities. And the idea behind mass is that, one, it is responsible for an object's inertia. We'll talk about inertia later. And two, it responds and generates gravity. Responds to and generates its own gravity. Okay. So mass is another basic quantity. These last two are debatable. That I'll give. Temperature. Now, temperature is it's something that is very perceptible. You can perceive temperature differences very readily. Like your human sensory apparatus is very fine-tuned to perceive temperature, and thus temperature was measurable fairly early. We now understand that temperature can be determined, or temperature, the phenomenon of temperature is actually a result of motion. We'll get into that when we talk about thermodynamics. But basically, temperature is an aspect of motion, which, as we'll discuss in a minute, is sort of a derived quantity of time and length. But temperature can be one. Another one is charge. Now, another interesting thing about charge is we don't have very simple ways to measure charge. Charge is most analogous to mass. It's an attribute of many physical quantities, or many physical entities. And a lot of times charge ends up being balanced in those physical entities. It's not they don't have charge, it's that their charges are balanced. And it responds to both electric and magnetic fields, generates its own electric and magnetic fields, things like that. However, a lot of times people will instead say current is the basic quantity. And this is for the simple reason that current is easier to observe. Current was one of the first measurable quantities associated with electricity that people were able to define. We'll talk about the relationship between charge and current when we get into electrostatics and circuits. But the idea here is that there's something, whether or not you think about charge or current as fundamental is, that's debatable. And it kind of depends what perspective you're looking at it from. Are you looking at it from, okay, these, with a more full understanding of the universe, these are
these are the fundamental attributes that can be measured, or are you thinking about it as from a discovery perspective, not knowing anything, this is what you would discover first? It kind of depends. So we'll get into how charge and current is measured. You may already know that if you've taken a circuits class, and many students in here have. So you may already be familiar with current in particular, possibly charge as well. But to talk about next thing I want to talk about is some derived quantities. And basically what derived quantities are is they are measurable quantities that are dependent on the basic quantities. So an example of a derived quantity, oftentimes what they do is they involve measuring two or more basic quantities in conjunction and understanding the relationship between those two basic quantities. So an example would be speed. Speed is basically a derived quantity that depends on some sort of length measurement and some sort of time measurement in tandem. Another one would be, say, volume. Volume ultimately depends on three length measurements in different directions. We'll talk about directions in the next class. Another example would be force. Now we'll get into force more, but basically what force is, in order to measure force, you're going to actually have to depend on mass, length, and time measurements in order to understand what force is. In order to really understand measuring force and how force is quantified. But this is the idea behind derived quantities. Now, I want to talk a little bit about units of measurement. And the idea is I'm only going to talk about the basic units of measurement. As we introduce new units, we'll go from there. But the most common is the metric system. And then you also have the imperial system, sometimes called the British system. I've always liked the imperial. The imperial system makes me feel like I'm in Star Wars or something. Now, for time, it turns out they're both the same. It's the second. The second just turns out to be a very useful unit of time. I did have a question now that I'm thinking about it. Somebody wrote in the textbook, why is you can build more units of time. You have 60 seconds in a minute and 60 minutes in an hour and 24 hours in a day and 365 days in a year. Why is time not metric? Well, I mean, the idea is that some of them it's clear why it's not metric. Like a day is a very clear unit of time. The idea behind a day is that it's one cycle of the sun. That's just very very straightforward. And the idea behind a year, this is how many days it takes for basically for the night sky to look identical to how it looked 1 year ago. That's I don't have time to get into all of that right now, but that's the idea. We know now that corresponds to a revolution around the sun, but before people understood the concept of year, long before they understood the heliocentric model of the solar system. So day and year, that's how that works. Like for a month, well, that is actually the cycle of the moon. So that's another physical phenomena. A week, well, the moon cycle was divided into 4. So, it starts, we generally think of when there's no moon in the sky, that's the new moon, no moon. And then, you can get we call it the first quarter. It's really, half of the moon is illuminated. That happens in about a week. And then the full moon is illuminated. That's another week. And it goes back to half. It's the other half. That's another week. And then it goes back to new. That's roughly another week. Now, it's not perfect, but that's kind of where that thing those things come from. So a lot of the time units they're based a lot more on experience than they are on ease of calculation. We'll actually see this is true in the imperial system as against the metric system itself. Okay, so when it comes to minutes and seconds, the number 60 is super convenient because it is divisible by 2, 3, 4, 5, 6, and 10. 10. But the idea of having it be divisible by the first six numbers, I mean, one is obvious, but it makes these things makes a lot of the calculations a little bit easier. So when you see 60s cropping up, this is why. It's because of the ease of divisibility when you have your number, your unit of time being divisible into 60. You go smaller than a second, you do start getting into the metric prefixes. So in physics and in chemistry and many other sciences, we want to look at time scales smaller. We go smaller than a second, we don't come up with additional units. We start putting the metric prefixes on it in order to indicate smaller. So like a femtosecond, that is 10 to the negative 15 seconds. Okay, so that's kind of where that comes from. Mass. The imperial unit of mass is kilograms. The imperial unit of mass, people will often say is pounds. It's incorrect. It is slugs. Pound is actually a unit of weight, which is a measure of force. We'll get into the distinction a bit later, but slug is a very seldom used unit. It turns out mass and weight are readily converted as long as you're situated on the surface of the planet Earth or near it. When you start dealing with other things, it gets to be a little bit more complicated, but that is another distinction between imperial and metric. Mass is often used to describe weight in metric. The unit of I'll indicate this. The unit of force, put this in parentheses. This is a pound for imperial. The unit of force for metric is the Newton. Now, the thing is that when someone reports, a society that uses the metric system, when they report their weight, they give it to you in kilograms. So they're actually giving you their mass rather than their weight. They don't tell you how many newtons they weigh. Strictly speaking, in the metric system, you should use newtons, but you'll notice that the conversion, there's a conversion between kilograms and pounds. They are they are different units, but as long as you're on the surface of the Earth, the force and mass, or weight and mass, are directly related. And we'll get into why that's the case. And then, of course, length. The fundamental unit of length is the meter, and the fundamental unit of length in imperial is the foot. Now, you can talk about different fundamental units. Like you could say the inch was fundamental. In metric, it's very easy to know what the fundamental is because it doesn't have the prefixes. You can take a look at Appendix C. So metric prefixes. This is you can find these in Appendix C in the textbook. You can just click on that if you just click on the textbook in perusal. And you can see all of those. But it's the fundamental metric unit if there's no prefix. If there is a prefix, then it's a derived unit. And if you dropped that prefix, not a derived unit, but it basically has a multiplicative factor. So milli is 1,000th, kilo is 1,000. You can go check out the other ones if you're so inclined to do that. Okay, so that is, I think, that is all I wanted to say about measurement units. I also want to talk about measurement reporting. And I think this is going to be it for this lecture. We'll get into more of this a bit tomorrow. Now the thing is, the thing that I want to talk about here is that when you give a measurement, you communicate two things. And these are distinct things. All right, so two distinct things. The first one, the obvious one, is just the value of the measurement. But the other thing that you are also communicating, and this tends to be a little bit more nebulous. People are not as precise with this idea of it, but you're also communicating something about how certain you are of the measurement. All right. So let me try and show you what I mean here. We could, if we were to measure Mr. Rin's height, we could say the following things. We could report it the following things. We could take a glance at Mr. Rin and we could say around 6 feet. Now, strictly speaking, what this means is again, we know that I'm around 6 feet, but we could reasonably say that I am greater than 5.5 feet and less than 6.5 feet. Okay. When you say around 6 feet, that is sort of what you're saying. Now, typically, if you're reporting someone's height, you do a little bit better job than that. So you would get, typically what you'll do is you'll give a number of inches. Now we'll use a combined unit like 6'1", 6'5", 6'7", whatever. But a way to report that would just be to report the number of inches. So the second way we could do it is we could say 72 inches. Now, if we're saying this, basically what we know is that this is it's greater than or equal to 71.5 inches, but less than 72.5. Okay. So what we're saying when we say 72 inches is these are basically saying the same measurement, but one of them, we're being much more certain about where we're located in this measurement. Okay, we're being much more certain about where we're located, and I'll get into that. We're being much more precise. That's the sort of academic way to say that. We could also say, okay, 71.8 inches. I think I'm a little shorter than that, but whatever. Now, if we're saying this here, basically what we're saying is that my height is somewhere between 71.75 and it's greater than or equal to 71.75 and less than 71.85. So the idea here is that my actual height should round to this number. Okay, my actual height should round to this number. So these would be feet and these ones would be inches, but whatever, you get the idea. However you report it, your actual height will round to that number. Now, again, it leaves some uncertainty about what it actually is, but there you go. Now, if I said something like this, 71.784632198617 inches. If someone were to report this, I'll tell you what they are full of. And the whole point is that there is no way, we do not have a measurement system precise enough to be this certain about my height. Okay. There's no way. As a matter of fact, my height probably changes more than that with each beat of my heart. So there's no way we could know this precisely. That's what this measurement is. All right. Now, sometimes this will happen when you calculate things and the calculator will spew out a bunch of decimals. And this is where this idea of significant figures comes in. I'm going to get, I suppose I can try and knock that out. Well, I'll go over the specifics of the significant figures rules in the next lecture, but this whole idea is that this is why significant figures are relevant, because what you don't want to do is you don't want to report some calculation with way too many significant figures, because not only are you reporting the value, you're also communicating that you know it this well, that you know it to, how many did I write here? I wrote 6, 9, 12, that we know my height to 12 decimal places in inches, and there's no way we know it that well. Okay, so when you think about the purpose of significant figures, I never got the purpose when I was taught about significant figures. I never got the purpose of it, but this is the purpose of it. Okay, it's to make sure that you're not claiming something that you don't actually know. All right, so that's what that is. Since I brought up the term precision, I just want to talk about accuracy and precision. Accuracy and precision. The standard definition, if you've heard this before, is that accuracy is close to actual value and precision close to other measurements. Now, I want to flesh this out. This is not incorrect, but it's a little bit I've always thought this is a little pedantic, because like, how do you know if something's accurate? Well, if you know what the actual value is, that's fine. And if you're, if you're shooting a rifle at a target, you know what it means to be accurate because you know the actual value is the bullseye of the target or wherever you happen to be aiming on the target. Like, that's the actual value. But if you're making a scientific measurement, you might not know what the actual value is. Okay, so the idea here is that what you can know is you can know something about precision. And whether or not you're shooting a gun or making a scientific measurement, you can know whether or not the instrument is precise. And the idea is that with repeated uses, you get something close to what you got before. So if you're shooting, a rifle that's good and you're a reasonable shot, what you'll have is you'll have a tight grouping. That means the instrument is precise. Now, it may not be accurate. You may be, it may be high if you're not sighted incorrectly, or low or whatever. But the instrument is precise. That's the idea. Same thing with a scientific measurement. If your instrument is precise, then you'll measure something and you'll get close to the same value each time. Now, your instrument might still not be accurate. Just like if your rifle isn't sighted incorrectly, if your instrument isn't calibrated correctly, it might be off from the actual. And if you're making a new kind of measurement where you're not sure what the actual value is, well, you don't really have a way to know whether or not it's accurate. However, if your instrument is precise and you can take multiple different kinds of measurements with precise instruments that converge to a single value, that is how you determine whether or not something is accurate if you're not sure what the actual value is. Okay, so that's a somewhat long-winded, take on accuracy versus precision, but I'm going to go ahead and leave things there. Next class, I'll do the significant figures rules. We'll talk real quickly about scientific and engineering notation, and then I want to do some of the math skills that we're going to need in this class, along with an introduction into vectors. Okay, so thank you for joining me. I'll see you next time.